Okay, recording has started. So I'd like to welcome everybody back to the next session where we will have Dr. Federico Cairoli, who will be talking about the introduction to survival data in the Kaplan-Meier analysis. Over to you, Fede.
Thank you so much, Buhle. Well, yes, I am Federico Cairoli, part of the scientific committee on R-HTA for LMICs and senior health economist at Triangular Health. So before going to R, I would like to recap on the main principles for overall survival. So you can see here one survival curve published in one paper in New England Journal of Medicine. It was a randomized clinical trial. And for this graph, I would like to highlight some specific things. First of all, in the y-axis, you're going to find probability of overall survival, while in the x-axis, you're going to find time. In this case, months since randomization. You're going to see also that we have two different curves, one curve for the treatment, another curve for the comparator arm. And there are some specific measures that could be important here. Sorry. First of all, let's take an example. So basically, imagine that we would like to check what about the probability of overall survival at month 15. So we can see that for the treatment arm, at month 15, the survival probability is approximately 87%. While in this same time, we're going to find that for the treatment arm is lower than 80%. Another measure of importance here is this median overall survival. This is at which specific time we find that we have 50% of our cohort still alive. So in that sense, if we would like to estimate the median overall survival for the comparator, we have to check approximately here is 31.8. You can see this number here, while for the treatment arm is higher. In this case, is approximately 38.6. So we know that on average, the people on the treatment arm is going to live more. Another measure that we can use here is the hazard ratio. So you should be familiar with this specific measure. But basically, the idea is that if we compare the hazard of the treatment arm with the hazard of the comparator arm, we can obtain values higher than 1, which means that the treatment is less effective than the comparator, or values lower than 1, which means that the treatment arm is better in terms of, in this case, overall survival. One thing that is important to highlight is that what is hazard? How we interpret hazard. Hazard is basically total number of events on average per unit of time. So imagine that on average, I don't know, it's just an example, on average for the treatment arm, we found that we can estimate 10 events per month. On the other hand, imagine that for the comparator arm, we find that on average, the hazard is 20 events per month. So in that sense, the treatment arm is going to have half of the hazard than the comparator. In other terms, the hazard ratio will be 0.5. And the last thing that I would like to highlight here before going to R is that I think that Hosh mentioned that before, but every time in the curve that you will see this drop, it's talking about that patient having events. While these specific marks that you are going to see here are representing censoring. What is censoring? Basically, until this point, we have information of one specific patient, but then we just lost this patient. We don't know if this patient is going to be alive across the time or not, but we just have information for this patient until this point. So we are going to use this information. We are not going to lose this information, but we are going to censor this patient. And the last thing is that usually in these survival curves, in these clinical trials, you're going to find the number of patients at risk. So you can see that, for example, in the treatment arm, the clinical trial started with 279, while the comparator with 277. And the idea is that every time, of course, one patient is having the event, in this case, death, you're going to have a lower number in the next interval of time. While when you also have patients that are censored, also this specific effect is going to impact this number of patient at risk. So given said that, we can go to R. So you may find this specific script in the GitHub, but basically we are going to use some specific package that have specific databases or data sets for that we can use to conduct Kaplan-Meier curves and also to do survival analysis. So first of all, you have to install this package, and I am going to activate these libraries as I did before. So every time that you open RStudio, you have to activate the libraries. If you have installed this package before, there is no need to do it again, but you have to activate the libraries again. So to begin with, we are going to use this specific database, which is called AML, Acute Leukemia Survival Data. So we just put this name in R, and if you have installed this and activate this specific library, survival, R will understand that you mean to this specific data set, which has basically 23 observations, one column for time. This is the time of follow-up. One column for status. 0 is patient is still alive. 1 is the patient had the event, in this case, death. And what about the treatment? If the patient received maintained or was not maintained treatment. By doing that, what I am doing basically is replicating the same data that is available in survival, but as one of my objects, in this case as a data frame. So we can see also this information here. And we know that we have information for 23 patients, each of these rows, with 3 specific variables, as I explained before, follow-up, status, and also the treatment category. The next step here is we are going to try to replicate the same survival curves that we have already seen before using this example of this clinical trial published in the New England Journal of Medicine. So to do that, we are going to use this function, which is surfit. And we can look for some help. We can do it in 2 ways. One is the same that I think Hosh already showed, using this specific code, or also we can go to help here, and here just to put the name of the function. In this case, surfit. So we obtain this specific information for this specific function, surfit, from survival package. And basically, you are going to read some description, usage, and also details. The main point here is that this specific function is going to replicate these Kaplan-Meier curves, but will need some information. And this is when this formula appears. So basically, the formula that this specific function needs is a formula in which we can tell our what about the follow-up time, what about the event for each of our patient in the database. So to do that, we put the name of the function, we open parentheses, and we start with one way to define this formula is using another function, which is called serve. And here again, we can go to find some information about this specific function. So again, we put survival because survival is the name of the package, and then serve. And we are going to see that, well, this specific function is useful to define this formula that I mentioned before. And basically what this sub-function needs is time, data on time, and data on event. Remember that we have this data from our data set here: time, follow-up time, and event. So what we are going to do is we start with this surfit function, and then we use this sub-function serve, and basically we are going to fill all the arguments, the main argument that this specific sub-function needs, which are time, and we put time equal to, and then we are going to put the same name as we have in the database that we are going to use. So for follow-up time is time, okay? Because basically this is the name of our column. If the name of our column was follow-up, we just put here follow-up. But since the name is time, we put time. Then we put comma. The second argument is event, so we put event, and equal to, we are going to check that the name of our column that has this specific information is labeled status. So event equal to the status. We close parentheses, and then this specific function, surfit, is going to need this operator to give some information if we would like to stratify this Kaplan-Meier curve by another column or not. In this case, we can do that. We can stratify and have two different Kaplan-Meier curves, one for these specific treatment categories, and the other one for patient that has this specific treatment category. In this case, we are going to put one. We are not going to put the name of this variable to stratify, because to begin with, I just would like to see one Kaplan-Meier curve. Just one Kaplan-Meier curve for all these 23 patients, no matter if the patient received maintaining treatment or non-maintaining treatment. But I would like to see just one Kaplan-Meier curve for all these patients. To do that, we just put one. So R is understanding that there is no need to stratify by another variable. We are going to analyze the whole data set. And finally, we have to tell her which specific database that we are going to use. So we are going to use AML. We just close the parentheses, and this is a function that we are going to run. You can see that when you run this specific function, you are going to obtain this, brief information. First of all, the total number of patients, we know is 23, the same as we have here, 23 observation. Total number of events, 18. Basically, if we sum all these numbers, all these patients that have this event, we are going to obtain 18. And then the median overall survival, this same measure that I already explained with you when we saw this specific figure from the New England Journal of Medicine. And then the interval confidence around this specific median value. Okay, so that's okay, but we are going to need, or we would like to have more information. So what I am doing here is just basically creating an object with the same code that we saw before. So basically, we are going to have the same information that we saw before. But now what we are going to do is to plot these informations to have this survival curve. To do that, I am going to replicate this line 20 here. We use a function plot, which is common to replicate figures. Then we put the object that we are going to replicate in this figure, in this case, KM. And then we can add, for example, Y label names. We open comma and we put, for example, survival probability. And then X is label, in this case, time in months. So we put month. So I just replicate this specific function that we have below. So we run it, and we are going to see. So basically, again, survival probability based on the AML database, time in month. This is the central value, I mean, the principal Kaplan-Meier curve, and this one is a lower confidence interval, and this one the higher confidence interval. This is the survival probability for our data. And of course, since we are just using an N of 23 patients, we are going to have this big range of confidence interval around the central value. So the next thing that we can do, which will be very informative, is to read all this information around the survival probability in a table. So to do that, we are going to use another function, which is containing the survival package also, which is tidy. So we just write tidy, and then between parentheses, our object, Kaplan-Meier, okay? And we run it. So we are going to obtain these tables, these survival function or survival probability tables, which are really, common in the literature. You are going to see, you're going to find this specific table often you read about studies in survival analysis. So basically, the idea is that we are going to have time of follow-up here, number of patients at risk, total number of events per interval, total number of sensor patients per interval, then the estimate of the survival probability, the standard error around this estimate of survival probability, and the confidence interval high and low for this specific value. So the point is that you are going to see here just those time points in which we have or an event or a sensory. In this case, we have or event or sensory just at month number 5, 8, 9, and so until 161. And how R is obtaining this survival probability is obtaining through the Kaplan-Meier approach, and the formula to do that is very, very simple. It's basically dividing the number of events by the total number of patients at risk. Since we are talking about survival probability, we are going to do, and I am going to open another script here to do the math. So basically, this is 1, because we are not talking about hazard, we are talking about survival. 1 minus 2, the number of total events, divided by the total number of patients at risk, 23. If we run this, we are going to obtain the exact number that R is showing here. What happened in the second interval at month number 8? From month number 5 until month number 8, we have the same survival probability because we didn't have any event or any sensory. So here is practically the same. So we replicate the same formula, but the only difference is that we had 2 events, but the total number of patients was 21 or 23 because we just 2 patients has died. So have died. So basically it's 2 divided 21. If you run it, you are going to obtain 0.90, which is not the same value as R is showing here. Why? Because this value is the product of these two numbers. So every time R is showing information for next interval, this is the accumulative survival probability. So basically what you have to do is to multiply this value by this value, and you're going to obtain the same value that R is showing here. If you do the same, you're going to reach the final value. This is again, the survival, how to estimate survival probability. One more thing here, that is important, is that, for example, here at month 16, we didn't have any event 0, so there was no death at all, but we lost one patient. So you're going to see that the survival probability is exactly the same, because this patient, I mean, is maybe still alive, but we just lost this patient. This patient is not dead. So the survival probability is exactly the same. But the only thing is that in the next interval, we are going to start with 14 patients at risk, no 15, because we just lost this patient. And we just continue with, again, number of events divided by 14, and then we multiply. This is the product of all these specific formulas. So this is how R is estimating the survival probability. So we close this and we continue with our script. Well, so if you remember, we said that to begin with, we just were interested in to know or to replicate the Kaplan-Meier curve for the whole data set, which again is AML. But what if we would like to see two different Kaplan-Meiers, one for the maintained groups and the other one for the non-maintained group? So we are going to put the name, instead of putting 1, we are going to put the name of the column. In this case, the name of this column is X. So basically, this is exactly the same code as we have here, but instead of putting 1, we are going to stratify by treatment category. Of course, we are creating another object, which is not KM, is km.x. You can put any name that, any name that you would like to put. I just decided to put km.x. So we run this specific object, and we are going to have this specific information here. Then we are going to again to see this summary here. You remember that originally when we did that, we just have this specific information for the whole cohort, n equal to 23, 18 events, the median survival for the whole data set. Here we are seeing information stratified by treatment category. So for the maintained group, we have 11 patients, while for the non-maintained group, we have 12 patients. You can see also the total number of events and the median survival with the confidence interval. Here we are seeing a not available because we are working with a really low sample size. This is why we cannot see the entire confidence interval around that. So you can see here that, for example, the median survival is higher for the cohort that was using this maintained treatment. So let's do the same as we did before. We are going to replicate the plot here, but instead of using KM, which was this specific information for the whole data set, we are using km.x stratified by treatment category. So we are going to run this, and you're going to see that we have now two different Kaplan-Meiers, one for the treatment arm and the other one for the control group. Again, and it's every time that we have this drop, it's because we had an event. Let's do the same for the table. So if we run this tidy using km.x, we are going to obtain, again, the same structure, but stratified by different treatment. So here we have patients that receive the maintenance treatment, and here we have the control group. But then all the sequence is exactly the same, and I explained before. So let's go. The next thing is that we can improve a little this Kaplan-Meier curve until we can have this Kaplan or these survival curves similar to the one that we have seen for the New England Journal of Medicine. How we can do that? So we can start. So basically, this is the same code that we already ran. So what we can add to this code, first of all, is this function within this function of plot, which is confidence interval. And the confidence interval, if you put false or F or false, is basically not giving you the confidence interval, while if you put true or just T, you're going to see the confidence interval around these specific Kaplan-Meier curves. And also we can add colors, in this case, red for the comparator and blue for the treatment arm. So by doing that, if we run this specific function, we are going to obtain different colors for, and also the confidence interval. Let's avoid the confidence interval to understand better again. Sorry, red one for the treatment arm and blue one for the comparator in this case. And there is another function which is more complex than this plot, which is called GG surplot. So basically, if you active these libraries that I already shared with you, you just have to put the name of this function, and again, between parentheses, the name of the object that you would like to replicate the graph, and we can also see the confidence interval true or false. We are going to start with false, and we are going to run this, and you can see that, well, first of all, is cooler, and then we are going to see that we can see here also not only the events, the drops, but also the sensoring data. So for example, for the treatment arm, we can see that we have one sensoring here at time, I don't know, 20 something, then here almost 40, and then here 160. And if we recap on the sensoring, we have this information here. So we have one sensoring at 28, which is this one that I already shared with you, 28. We have one sensoring here, 45, which is this one, if I'm not wrong, and this one, sorry, 45, and 160, 161, which is this one. And the same for the comparator. You're going to find this sensor patient using these marks. So in that sense, this specific plot is better. And what we can add also is the risk table that we have seen before for the New England Journal of Medicine. So what we have to do is we put confidence interval, true or false, and then we put risk dot table equal to true or false. If we run it, in this case, it will be, if we go with the confidence interval and also with the risk table, you're going to see this. So basically, the total number of patients at risk at 0, 40, 80, 120, and 160. And again, the Kaplan-Meier curves with the confidence interval. If you would like to see not see the confidence interval, you're going to see this. But the confidence interval may be of importance because you may guess that you can see here that the confidence interval for the Kaplan-Meier curve of the comparator is included in the central value of the Kaplan-Meier curve for the control arm. So you can imagine that there will be no difference in statistical terms if we compare these two different curves. In other words, the treatment is not having any effect in this cohort. How to do that? So we can run one specific test, which has this name, long run test, which is basically a chi-square test. So basically the idea is that this test is going to compare the observed and the expected number of events per each interval, and then putting all together to obtain a p-value, a chi-square value, and finally a p-value. You can see that to run this specific test, this is again to compare to be sure if there is a statistical difference between these two arms. So to run this specific test, we run this specific serve diff, and you can see that then the structure of this specific function is practically the same as we have seen before. Time equal to time and event equal to status. Okay, and then of course stratify by treatment using the same database that we have been using before. So one more thing is that if we would like to do this to have more information on subdiff, not sure if you can find here the null hypothesis or the alternative hypothesis, but basically let me show you. If you run this specific test, what you're going to see is for each of the treatment categories, the total number of patients, the total number of observed events, expected events, and then all the calculation needed to obtain this chi-square value. So you can see that the p-value in this case is higher than 0.05. The null hypothesis here is that there is no difference at all in the experience of the event of these two Kaplan-Meier curves, as we were expecting when we saw this specific, the confidence interval, and how the confidence interval is crossing the central values of the other Kaplan-Meier curve or survival curve. So in this case, we cannot reject the null hypothesis. So there is no way to reject that there is no statistical difference between these two arms. In other words, there is no effect on the treatment. So you imagine that instead of saying 0.07, you see, for example, 0.03, just below the threshold of 0.05. So, okay, so maybe there will be a difference. There will be some effect or impact on the treatment, but how about the magnitude of this effect? And this is when the hazard ratio comes. And if you remember, we just explained that the hazard ratio is basically the difference or the ratio of the hazard on the treatment arm divided by the hazard, total number of events per unit of time, divided by the hazard of the comparator, total number of events per unit of time for the comparator arm. So how we can obtain a hazard ratio using R? So again, here we are going to continue with the same database, which is again AML, and we are going to obtain hazard ratios using this function, COX-PH. And again, you can see that the structure of this function is always the same. We are putting the serve subfunction to define time, event, then this operator to stratify or not. If we don't want to stratify, we put 1. Here we want to stratify to see the hazard ratio of the treatment, and also data equal to the data set that we are using. Okay, so basically we just run this specific function. You obtain this specific output, but we can obtain more detail, including all this information, if we create an object. In this case, I just put this name of ml.cox. Here, we are putting the same code that here, okay? But we are just assigning this function to an object. And then to use this summary, basically summary, and between parentheses, the object with the Cox model. This is a Cox model. As when you run a logistic regression or linear regression, this is the Cox model that you can incorporate not only one variable, but also to have multi-variables. So we run the Cox model, and this is what we obtain. First of all, the total number of patients, 23, the same as we have originally, 23. The total number of events, 18. It's important to always check this number because sometimes the event status, maybe you may have 0 for, I don't know, no 0 for death, but maybe, I don't know, 1 for death and 2 for censoring, and you may have more information. So you have to be sure that this number is, this function is understanding well that how you categorize this specific variable is okay. So total number of events, 18. This is what we were expecting. And then we obtain this information. Since we just remember that after this symbol, we just put X because it's basically the unique extra variable that we have, regardless time and status. But you may have a lot of different variables with age, information on age for each patient, information on sex for this patient, for example. In this database, we just have treatment category, okay? So we are going to see just hazard ratio for the treatment category. So this value coefficient is the beta value. You have to do the logarithm of this value to obtain the hazard ratio. The only thing is when you see this value, if you are going to see that this value will be positive, it means that the hazard ratio will be higher than 1. If this value is negative, so the hazard ratio will be lower than 1. And this is the hazard ratio. So we obtain a hazard ratio of 2.49, which means that patient or the cohort that received this non-maintained or didn't receive a maintained treatment basically have 2.5 times more hazard than the treatment arm, the patient or the cohort that received the maintenance treatment. But well, we have said that when we ran the univariate analysis, when we saw also this Kaplan-Meier curve, we didn't find any statistical difference. And if you see here, this is the same p-value that we obtained before when we ran the long-run test, and basically saying that the same. So it's higher than 0.05. And here you will find the lower and upper confidence interval. So if you see, the hazard ratio again is 2.5, 2.49, but the confidence interval could go from 0.9 until 6.8. So since this confidence interval crossed the value of 1, so the treatment could have benefit or not. So we can't, the same as we said before in the long-run test, we can reject the null hypothesis that there is no difference between these two Kaplan-Meier curves stratified by treatment category. And then we also have some data here. Basically, these three are saying, okay, so basically your model overall is useful to predict or not. And basically we obtain a p-value higher than 0.05. If we will have, for example, one specific variable here that has a p-value lower than 0.05, so maybe one of these will be lower, or maybe some of them or most of them will be lower than 0.05. And this value concordance basically said that, well, if you have a concordance value close to 1, so basically the prediction, the accuracy of your model will be really high. If you have this number close to 0.5, it will have accuracy. So in this sense, so we cannot say that it has a high accuracy. But the more important test, we can see that, so basically our model is not useful to predict that this specific variable is having an impact in our data set. So just before we go to the breakdown session, I am going to show you one more thing. So basically, we stop here with the summary. And then one thing that we were discussing before is that to run this specific Cox model, we have to be sure that the assumption of proportional hazard is not violated. So basically, I remember that Hosh explained this in detail before, but we have to be sure that the difference or the relationship between these two curves is practically similar, proportional across the time, and one curve is not crossing the other one, for example, at early time. Okay, so this is very important. Why? Because when we say that the hazard ratio is 2.5, we are going to say that this hazard is going to be 2.5, no matter that you are looking for this specific time point, this one or this one. You are going to find this specific hazard for the whole Kaplan-Meier curves analysis. Okay, so if you have this line that cross this one and then cross again, so you can't say that overall this hazard ratio is the value for the entire analysis. So to be sure that in this case, we can see by visual inspection that, I mean, we are not seeing this curve crossing, but we can run a statistical test to be sure that this is, again, in this case, we know that our model is not saying that the treatment has an effect because the p-value is higher than 0.05. But still, we have to check if the model is accurate. Imagine that in this case, the model is saying that the p-value is 0.03, and in fact, the treatment has an impact. Okay, but then it is okay to use this specific model based on the proportional hazard, or this proportional hazard assumption is violated. So to do that, we use this specific function, which is cox.zeta-ph, and then again, the same object that we have here when we define our Cox model for MLL, and we just run this specific function. You will see that, I mean, it's very brief what you obtain. Basically, a p-value of I have some information here. This specific test, so the null hypothesis is that the covariate effect, in this case, we are just analyzing treatment as the covariate because we have just one additional variable besides the time status. The null hypothesis covariate effect is constant proportional over time. This is the null hypothesis. And to do that, we are running a chi-square based on Schwarzschild residuals. So basically, we are saying that this value is higher than 0.05. So if so, we can say that there is no violation of this assumption. And if we plot this specific function, if we plot again, we are going to see this. So you can use both, not only the statistical test to say, okay, see, look, my model is not violating this proportional hazard assumption, but also you can base your justification using this specific, or showing this specific figure. So basically it says that, remember that the coefficient was 0.9. I mentioned that if this coefficient is positive, so the hazard ratio will be higher than 1. If this coefficient is negative, the hazard ratio will be lower than 1, okay? So basically, we can see that across all the time, the beta, the coefficient, is not going below 0. Or if it's go lower, maybe just 0, but not going too much lower 0. And then on the other hand, its value can reach 2 point something, okay? And of course, this 0.9 is an average of all these fluctuations. Okay, so we will expect a flat line to say, okay, there is no fluctuation at all. So basically, our covariate effect is 100% constant, but you may expect some fluctuation. Of course, the point here is that this rotation is not crossing too much this zero, because if so, you are going to have at some point a hazard ratio higher than 1, but at another point in time, you're going to have a hazard lower than 1. And then it's why this specific proportional hazard assumption is violated. But again, we have here a statistical test saying that this value was higher than 0.5, and then you can also check using this information. As I always said, you have to use both the statistical test and also to have some visual graph to check this specific assumption. So this is how we obtain the Cox model. If we have time, I am just show you an example of what happens when we have multi-variables, a multi-covariate Cox model. So we are just using as an example this Lang database. Let me run it. So you will see that we have, again, information around time, status. In this case, time is in days. Status in this case is one. Let's check because I not completely remember. So again, this Lang database is within the survival package. So we just put this in here, or you just put here Lang, and you're going to obtain the description of the database. So time in survival, time in days, the status sensor in status 1 sensor to death. Okay, so we have this specific information. We are also going to use age, sex, male equal to 1, female equal to 2, and weight loss, which is weight loss in last 6 months in infants. So basically, we have this database, and what we are going to do is to have, again, the Kaplan-Meier curve, the same thing that we did with the other database, in this case with Lang. And as I'm putting 1 here, I would like to see the Kaplan-Meier curve for the whole database, not stratified by any other covariate. Okay, so I just create this object of km.lang. Okay, and again, the tidy table. This is one more time to estimate the probability, survival probability. And then if we put just plot and km.lang, we should be able to see this Kaplan-Meier curve with the confidence interval. So again, this is for the whole data set, not stratified by any covariate. So what if we would like to stratify in this case? Imagine that this is not coming from a clinical trial, but it's just a real world evidence study. You are not interested to assess the impact of a treatment, but you would like to see if age, sex, and weight loss will be predictors of hazard or survival probability, or survival or hazard function, for example. So what we are going to do is the same when we created the Cox model for this other data set. But in this case, after this symbol, we are going to put 3 variables. Remember that in our original data set, we just have X as the treatment category. But here, let me show you also Lang as a data frame. So here in Lang, we have we have time, status, and different covariates. We are going to put focus on age, sex, and weight loss. Okay. So to add, after adding age, to add more covariate, we put the symbol instead of comma. And then, of course, we are now using this specific Lang database, not the acute leukemia database. So we run this specific function. And if you remember here, when we did it the same for the other database, I said to you that, okay, so if we assign this specific function to an object, and then we just run the summary for the object, we obtain more information. We are going to do the same here. So basically, we run the Cox model. We assign this Cox model to an object. In this case, I just put the name of lang.cox, and then we obtain the summary with more information. So now we are seeing that we have 214, which is the same as we can see here. So it's not the same. We have here 228. This is because we have not a NA, not available data, missing data. So you can see that there are 14 observations delete due to missing. And then we have a total number of events of 152. So again, this is important here to check if R is understanding well that, let's go again to lang. If in status, remember that 2 is death, 1 is censoring. So basically, to check that, what we can do is basically doing a sum. We just put sum. This is a function in R. There is no need to have a package here. And then we select the lang database, put this symbol to then go to one specific variable that you are going to look for some information, and put when status is equal to 2. And you will find, again, status is equal to 2 is death. So you will find that we have 165 events. If you put 1, this is the censor patient, 63 censor patients. So we can be sure that R is understanding well that these are the total number of events from this lang database. So here we have 3 different variables, not just one: age, sex, and weight loss. So you can expect that since age and weight loss are positive, so the hazard ratio will be higher than 1. And on the other hand, since sex is negative, the hazard ratio will be lower than 1. Okay, so how we read this specific value of 1.02 on age? So basically saying that for every age, for every age that you have in the model, the hazard will be 2% higher. In terms of weight loss, for every pound that the patient lost, the hazard in the last 6 months, the hazard will be this is 0.007075. It's practically nothing. And on the other hand, sex, if we go to sex again, this was female 2 versus male. So basically R is comparing 2 versus 1 and is saying that female has a hazard ratio of 0.59 compared with males. Basically a reduction of 40%, 41% of the hazard compared with males. And here you can check that the p-values are significant for age and sex, while for weight loss are not significant. And then if we check also the confidence interval, you may see that for the weight loss is crossing 1, while for age and sex is or below 1 or higher than 1. In this case, you see that these 3 tests are lower than, the p-value for these 3 tests are lower than 0.05. So basically, if we would like to check again with the statistical test, what about this specific proportional hazard assumption? We are going to find that any of these specific covariates has a p-value lower than 0.05. So you can predict that using this information, you can predict that in this lang database, when your patients are older, they will have a higher hazard compared with younger people, and females are going to have a lower hazard compared with males. And then we cannot predict anything with weight loss. But we can use this model because we are saying that there is no violation of the proportional hazard assumption. So, well, this was all. So basically the idea now is that you can, in different break room sessions, you can do some exercise. So basically what we are going to do in this break room session is that you are going to use this specific data set, veteran, which let's quickly see which information that it has. So basically information on time, status, while 1 is dead, 0 is alive. Also age, treatment, but we are just going to use information around time and status to begin with, and treatment also to begin with. In treatment 1 is control arm, if I am not wrong. You can check this information as we did before. So treatment stand control arm, and then 2 is the treatment of interest, or the test in this case. So we have 4 exercises. The first one is using this specific database, veteran. You are going to be, you have to generate a table of the survival function of the veteran data set, this Kaplan-Meier table that we have seen with these survival probabilities. Then exercise number 2, you have to plot a Kaplan-Meier curve using this data set for the whole data set, not stratified. Then exercise number 3, you are going to assess statistical differences by treatment, by this variable TRT. And finally, exercise number 4, using this database, you are going to create a Kaplan-Meier plot for the veteran dataset stratified by treatment. Not only statistical difference, but also creating or plotting this Kaplan-Meier curve. I just finished. Buhle, you are mute.
Sorry, thanks. Thanks, Fede. There's a question from Naela that says, should we add interaction term between covariate to this function? I don't know, Naela, if you want to maybe unmute yourself and ask a question. If not, Fede, are you able to answer that?
But yeah, I think that I understand the question. Yes, so basically we are going to see this in the next workshop. So we just saw that this proportional hazard assumption was not violated using these specific databases, but you may have one specific data set and you can discover that in your data, you're going to see this violation. So how to solve for this violation? So you can stratify, for example, imagine that, let me go to, do we have time, Buhle? Yes, right? Let me go to my R one more time. So imagine that we have here this information, and imagine that in sex, so you obtain a p-value of 0.04, and then when you see this plot, you see that there is no flat line there, and you say, okay, so I can't run my Cox model using this variable because, the model overall is violating this specific assumption. So to solve that, what you can do, first of all, is stratify by sex. So basically you run one specific Kaplan-Meier curve for males, another for females. And then if age and weight loss, if the p-value is okay, so you're okay. So you can, of course, you have to report information of age and weight loss for each of these sex categories, but you can report this specific data. And then you can conduct this interaction, as you mentioned. But again, these two possibilities are these two pathways. We are going to teach them, to explain them in the next workshop, not today.
Thanks, Fede. Appreciate it. So, okay, there's another question from Giovanni. How many variables can we plot from the model?
not sure if I understand well, how many variables can we insert into the Cox model? Okay, so in the Cox model, you can insert, you can always have to remember that in this logistic model, progression or linear regression model or Cox model, there should be an equilibrium between the total number of sites that you have, total number of events, patient, with the total number of variables. You can't put 10 variables while you have maybe, I don't know, 23 patients, because so then the accuracy of the model won't be good. But if you can find this trade-off between total number of variable, and if you have a higher sample size with a high number of events also, you can add more variables. And for the plot, if you are talking about this proportional hazard assumption, when you run this plot, you are going to see the same plot that I show you for the treatment for every variable. So basically, automatically R is going to show you for every variable that you are incorporating into the model.
Thanks, Fede. Thanks, everyone. We're going to go into breakout rooms. Sorry, I'm just stopping the breakout